Alright, so in this video we're going to take a look at the permanent magnet synchronous machine. Now, the permanent magnet synchronous machine can be considered to be a special case of the induction machine, since the magnetic field produced in this case is produced by a magnet as opposed to a winding, which it is in the induction machine. In terms of the modeling, we can use the exact same equations. So the equations you see here are the same ones we had in the induction machines video, so if you haven't looked at that, I'll link that in the description below, and you should check that out before you move on to this material, because otherwise you won't know where these equations really come from. So this is the mathematical model in rotor flux, or dq coordinates, we said. So we have some parameters here. We have lambda m. We can call this the peak permanent magnet, no, not pp, pm. pm, permanent magnet flux. And we can say that LD and LQ are inductance parameters. Now that doesn't mean they're real inductances, but they are modeled as such. Now we have another sort of figure of merit here, and that's LD minus LQ indicates the saliency of the rotor. So it's the degree of rotor saliency, they say. Now when LD, so let's say when LD equals LQ, this is non-salient. And when LD does not equal, sorry, the first one was equal, this does not equal, this means it's salient. Now this is just a way of like categorizing and quantifying machines. Again, they're just names. If you say, what does salient mean? I mean, you can look at the textbook definition or the dictionary definition of that and find out what the word means. But these are essentially, these are words to describe different types of machines that you have. Now, what's important for us is that in most electric vehicles, the machine is non-salient. So LD does equal LQ. Now, if LD does equal LQ, that means this equation becomes Tm equals 3p over 4 lambda m isq, right? Since LD is equal to LQ, the first term disappears entirely, which is convenient. But there are some implications here, right? So we see that we have this as a result. We have this equation as a result of our situation. But we also want to look at let's look at the power losses for a second, and the electrical power losses, I mean. So let's say P loss E is equal to 3 times RS, which is the winding resistance, times the current, which is IS hat over root 2 squared, right? The reason I'm using this, using 3 here is because these are usually 3-phase machines, and that means there are 3 such windings, meaning the loss is triple what it would be for a single RS. And this results in 3 over 2 RS. Now this IS, remember, we can write IS hat as being equal to ISD squared plus ISQ squared, all under the root, right? So if that's the case, then you have ISD squared plus ISQ squared under the root, all squared, would just remove the squared, right? So we can just get rid of that square root sign there. Now, what are the implications here? So let's take a look. When you look at your torque, you see that the torque is dependent only on ISQ. Now you have lambda m and you have P, but P is a structure of the machine, is dependent on the structure of the machine. And lambda m is, again, fixed because lambda m is coming from the permanent magnet. So this lambda m is fixed, this P is fixed, meaning ISQ is used to control the torque. Now if ISQ is being used to control the torque, what that means is we don't really need ISD, right? Because it's not controlling any of the torque. But ISD is contributing to the losses. So if we want to minimize the losses, why don't we set ISD equal to 0? If we set ISD equal to 0, this loss becomes 3 over 2 RS ISQ squared. So now we've reduced the loss to be, I don't know, depending on how large ISD usually is. I mean, ISD could be as much as probably equal to ISQ. And so if that's the case, you could have halved the loss, reduced it by a substantial amount. This method of control, or this control strategy, or whatever you want to call it, is called the maximum, so we'll abbreviate that as max, torque per ampere strategy. Means we set ISD equal to 0 so that we get the maximum amount of torque per ampere that we supply. So we don't bother to waste any current in ISD because it's useless, basically. It just adds to losses. I mean, it has a use in some cases, but for the narrative that we're sort of walking through here, it doesn't. So the differential equations we have here can give us steady state equations. So if we set these derivative terms to 0 and write everything in terms of VSD and VSQ, we can develop these differential equations. So we have VSD is equal to RS ISD minus LQ omega R ISQ. And then we have a second equation for VSQ, which is equal to RS ISQ plus LD omega R ISD plus lambda m omega r. Right? Again, setting derivatives to 0, solve in terms of VSD. And we also know, we kind of hinted at this before, but we also know that Vs hat is equal to VSD squared plus VSQ squared, all under the root, and Is hat, I'll write it again here just for the sake of completeness, is ISD squared plus ISQ squared, all under the root. Okay? Okay. Now, before going on any further, I mean, this is a sort of practical note. Machines are usually given the machine ratings that you get. So if you ever see a machine, like you might have like a lawnmower or like a snow blower, and there's motor ratings given on them for voltages and currents and such. Let's say you have like a 300 volt, 250 amp machine. This means a line-to-line RMS rating. So what that means is Vs hat is actually equal to 300 root 2 to convert from RMS, and then divide by root 3 to convert to line to neutral as opposed to line to line. Right? And so this actually means this is 245 volts. And if you had the same thing for IS, you would say this is 250 root 2, and that would be 353. Now the reason I'm not dividing this one by root 3 is because line-to-line current doesn't really, I mean, line-to-line current in the configuration of the windings, there is no like line to neutral current. It's all line to line based on the configuration. Now if there isn't, then you could divide by 3 if it's in a different type of configuration, and that you can actually have a line to neutral and a line to line being different, but in most cases the line to line and the line to neutral are the exact same. So next we need to look at the operating limits, because this as we mentioned, this magnetic flux, or the permanent magnet flux, is not controllable, meaning we can't achieve field weakening. So the challenge in this case is setting up something that might resemble field weakening, but again, it's very limited as to the field weakening you can achieve, because lambda m is fixed. You don't control the magnetic field, but there are within some limits that you can, but even those limits are usually not a good idea, because you can cause damage to the machine that is irreparable. So operating limits. We have 2 operating conditions. What are the operating conditions, or the operating limits? Let's say we have one, we have IS, let's say we have some current, ISD squared plus ISQ squared. And this, let's say it's less than some maximum current IS max, right? And we can call this the ampacity limit, how much current the thing can supply or hold or carry, or whatever you want to call it. The second limit is on the voltage, right? So the voltage would have a similar limit for VSD plus VSQ squared, and this has to be less than or equal to, let's call it V max. And this limit is a function, or it depends directly on the inverter, right? Because we've only talked about these machines from the perspective of control or modeling and like theoretical stuff like equations, but you have to understand that the voltages we're applying to these machines are usually being generated by some power electronic devices. Those power electronic devices have limits on how they can operate, their total voltage, current, power, all these things. So you can imagine that this limit is essentially an inverter voltage ceiling. Let's say inverter voltage. Let's call it a ceiling, I guess. It's probably the best word for it. So the ceiling. So you can't exceed this value with your inverter, meaning that's as far as you can go. So if we want to plot this, and plotting things is usually a good idea, especially when you're trying to understand how things are related to one another. If you want to plot this, you can plot ISD and ISQ. So let's call this ISD and you can call this ISQ. And if you plot the first restraint, or the first condition, I guess, maybe we can use the circle tool here so we can get a bit of a nice, a decent looking circle. For some reason it came out a little choppy, but that's okay. But you have this circle, okay? And this circle is condition 1, right? So condition 1, we can call this the current limit, right? And the radius of this circle is going to be IS max, right? Because IS max is equal to ISD squared plus ISQ squared. You can then do a similar thing with Vs, right? So what I'm going to do is I'm going to assume that Rs is small because the losses in Rs are negligible compared to the behavior of the rest of the equation. And so if I ignore Rs, then I get that VSD is equal to minus LQ omega R ISQ, and I get VSQ is equal to LD omega R ISD plus lambda m omega R. Now I can write Vs in terms of VSD and VSQ, and then I can write VSD and VSQ in terms of ISQ and ISD, right? So I'm going to do that. So you'll get Vs hat. If you do that and simplify it, I'm going to skip a couple of steps here because they're trivial basically. You can factor out the omega R, and you'll have a square root here, minus LQ ISQ squared plus LD ISD plus lambda m squared. Now, I'm going to assume in this case that LD and LQ are not equal because when we derive such limits, you want to do it for the general case. I know we said at the top we have some special control strategy, but we're not doing that right now. In this case, we're only looking at the general case. This thing here is the equation of an ellipse. And the reason it's the equation of an ellipse is because in the general case, LD and LQ are not the same. If they are the same, then you have a circle. But more importantly, this term existing on this side means that this thing will not be centered at the origin. Instead of being centered at the origin, this will be centered at the value of lambda m, well, negative lambda m divided by LD. So we can draw a little ellipse, I guess. Let's say it's centered off somewhere like this, okay? And let's imagine that this point is its center. It looks like it's roughly the center. And this is negative lambda m divided by LD. And this thing is our voltage limit. Okay? Okay. What we then need to do is we need to understand that constraint 1, the current one, corresponds to the current limit circle, while constraint 2 is an ellipse. We call the voltage limit ellipse, if you want to call it that. So the region that both of them the union, I guess, of these two regions, and the union of these two regions is this region here, that both of them bound, satisfies both constraints. And therefore, that's the permissible area for which ISD and ISQ can be chosen or picked, or whatever you want to say. So the challenge then is, if we want to achieve field weakening, you have to have the smallest negative ISD that gives you a certain speed. or that given a certain speed, I should say, corresponds to a point in the region. So let me break that down, because I said a bunch of stuff and a lot of the stuff probably means very little. The value of omega r will change the size of this ellipse, right? So the radius of this ellipse, again, is directly dependent on omega r. If I increase omega r, this ellipse will become larger. If I make it smaller, it'll become smaller, right? So for a certain omega r, you have a certain region that you enclose, right? So you have a certain overlap between the light blue and the light green. So this yellow shaded area will increase or decrease based on the value of omega r. So for a given omega r, if you want to achieve that, and you want to achieve some type of field weakening, and so if we go back up to our general case, we'll see how that actually makes sense. Because remember, in the general case, LD and LQ are not the same, meaning you can control the torque by adjusting these values, right? So you can adjust the value of ISD for this, you can adjust the value of ISQ, and you can control the torque if these two are not the same. But you see here that the range over which you can do that, such that both of these requirements are met, is small, relatively speaking, and depends on omega r. So you're very limited in how you can control this stuff. Okay? Okay, so that's so much for the operating limits. I mean, because you want to understand how the field weakening applies here, and that is exactly where we'll leave it for this video. So let's take a look at what we did, because there was a fair bit of stuff here, although we didn't have a lot of apparent stuff, it seems. So we have these equations for the permanent magnet synchronous machine. We got these equations from the induction machine, right? We can say that in the case where there's a non-salient and a salient machine, you can simplify for the non-salient case, and you'll get this expression for your torque. Then we said that since the losses depend on ISD and ISQ, and ISD does not contribute to the torque in a non-salient machine, we can set ISD equal to 0, and we called that this max torque per ampere strategy. Then, based on the steady state equations, we can set some operating limits for the machine such that we can achieve field weakening if we want to. We see that this depends directly on the value of omega r, and would obviously depend on the value of ISQ as well, because ISQ is used to control the torque. Omega r is a command that you want to give, so you kind of have to choose ISD based on omega r and ISQ, such that you reach the balance of torque and speed that you want. So then we drew this circle, and this is a nice way to visualize this, because again, the more you the way you adjust omega r directly impacts this overlapping region. So for certain speeds, it might be that you can't achieve field weakening, or achieving field weakening would somehow damage something in your system. So I know this part's a little, I mean, it can be a little I guess complicated to understand, because it's fairly complex or fairly abstract, I guess, but I mean, and again, a lot of it has to do with control, but the main thing to take away from this is ISQ controls the torque, ISD is set to 0 in maximum torque per ampere, but if we want to have field weakening, we have a non-salient machine, which is the only way we can have field weakening. Sorry, we have a salient machine, which is the only way we can have field weakening. You use ISD. So ISD does field weakening when it's salient. When it's non-salient, which it usually is, ISD is 0, and you have max torque per ampere, and ISQ controls the torque. So if you have any questions, leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.